So I'm going to start right in by giving you a problem. Here is some data. It's actually the data on the number of acres burned and the percent of property at fire risk in 30 years that they predict in 30 years. And then there's the number of acres burned by state across the United States. So what do you notice? What do you wonder? Type it in the chat. I'm waiting for you guys to type something in the chat.
It actually, it kind of just showed up right before you talked about notice and wonder. So,
Okay. So they didn't get time to see it before I'm waiting for them to type things in the chat. Thanks. This will be interesting. Does anybody notice anything? You wonder anything?
they're mentioning, like, are there more states below Missouri down there? Are there more states in your table?
Yes, so Missouri, no, actually, I think we have them all here. Montana goes up to the top. After Missouri is Montana. I think they're all there. Okay. So I'm going to go on to the question that I posed to my students about, is there a relation between the number of acres burned and the region of the United States? So another way to think about this is, do we see a relationship between forest fires and regions of the United States? So I'm going to go on to the next slide. And here's what I actually do, both in class and when I'm working with teachers. I have a number line that's drawn on the board or the whiteboard. If that doesn't work, I just draw it on the wall by just posting papers that mark the numbers. And
yeah, let's see if this will change.
Okay. The numbers go on the number line from 0 to 2.4, 2,400,000. Has it changed yet, Steve?
It has not changed yet. But people who like spreadsheets and tables are really enjoying this slide. There it goes. There, it just changed. So if there's number line fans, they're now happy.
All right. So here we got this number line. And as I said, this is drawn somewhere in my room. If you have to, you could actually go out in the hallway and make one on the floor. And the United States has been, by the Census Department of the US Census, is divided into different regions. And in this set of regions is 9 regions that divides the United States geographically. And some of them have only 3 states in them, and some of them have, I think, Northeast has like 11 or 12 states in it. And every student gets the data sheet that you just saw. They get a state, so they might get Texas, and they get the number of, from their data sheet, they have the number of forest acres burned, and they get a yellow sticky note. So all the Texas students, all the South students get a yellow sticky note. All the Southeast students get a purple sticky note. And their task is to put their state's number of acres burned on this number line. So just think for a minute about what that might do and how that might look, and think about what might happen. So while you're thinking, I'm going to actually change my screen, but your screen isn't going to change for a while yet.
Yeah, I think we see, there are some people who still don't see this slide, I'm afraid, but
So the slide that is I'm just changing off of was just an illustration of what you might have to give out to the students. And now you should see a slide of students actually posting their sticky notes on the number line. So can you see that, Steve?
it is not there, Gail, and I'm looking at the chat and some folks, so it's changed for me. With you've got pictures of students on the number line, and I see some people now saying, yes, it has changed. So I think it's, yeah, super laggy, but all right.
Yeah. So when we say what's the problem here, we actually mean it's super laggy.
Correct.
But the problem in the classroom is what is the problem in the classroom? So the kids all have their little yellow sticky notes, and Jessica nailed it. She said it's crowded, and they're all piled up down at one end. So when this happens, I actually make my students go sit down with their little sticky notes and ask what we can do. So what are some of your suggestions? What could we do that might avoid the crowding of everybody down at that beginning of the number line? What could we do to eliminate that crowding?
Cool. A group by climate, that'd be interesting.
Oh yeah.
And take an average, like use a mean of samples. Someone mentioned changing the scale.
So my students don't know what an exponential scale would be.
Yeah.
Or a log scale.
Yeah.
So they don't know what that is. What might they suggest? So you guys pinpointed it. It's clearly the scale is wrong. So how could I grapple with this scale? And my students don't have a clue about really an exponential scale or a log scale or anything like that. What might they think of? Well, eventually, first they say, well, there's only one or two numbers that are really, really large. Let's just cut out a hole in our number line and just put those way over in the end and not have anything in between. And that always makes me a little nervous because you can't just leave things out when you're working with data. So Roberta is thinking about rescale the left end. So Roberta, how might I rescale the left end? And she wants me to put a zigzag in. I really would not like to put a zigzag in there if I don't have to. Is there a way that I can avoid that? How can I rescale? And eventually the kids think, and this is kind of hard to maybe trust, but eventually someone will come up with the fact that maybe I could just use exponents. If I could just write these numbers instead of using the whole numbers, if I could just write them in powers of 10, I might be able to look at this slightly differently. So Roberta said cancel, but no, I really like your beginning thing about I want to rescale so that they're not crammed together. I want to cancel. I want to find some way to do that. So I'm shifting now to another screen. But when the students start to think about what this might look like, if they wrote their numbers using exponential notation, because they are familiar with exponential notation, so they write all of their acres burned using exponents, and I make a new number line. And the number line is now 10 to the 0, 10 to the first, 10 to the second, 10 to the third, all the way out to 10 to the sixth. And I send my students back up to the board, to the number line. They have their little sticky notes. They all now go up to the number line. Steve, can you see the number line now?
Yep, and you've got your exponents there, and the powers of 10 are evenly spaced on your number line.
Yep. So now the students have room to put up their numbers. So basically, when they do that, they get a different picture that has all colored little sticky notes. And the color, remember, represents the number of acres burned in a state. And you can see, if you eventually get this, you can see the distribution by state. And you can see things like, oh, the Northeast, they're the light blue ones, and they pretty much are not really have a lot of acres burned by forest fires. You can see that the yellow ones are pretty much at the past 10 to the fourth. You can see that the purple ones are past 10 to the fourth. So we can kind of like get a sense of what the areas are. But the big idea here is that the students have recognized that in order to make sense out of this data, they had to rewrite rescale. And that lets us talk about what this rescaling does. And they have actually invented this logarithmic scale, so that they're looking at their numbers in terms of exponents, writing them out. And if you look at the distribution that I have now in this log plot that I actually used, you could do it on either an 84 or on an Nspire. You can actually see this original distribution of the acres burned, and then you can see what this transformed when you just use with those exponents, what it looks like. And it's very similar to the picture that we just saw. So let me go to just another way to look at this. This is just using the Nspire and just looking at them by region. You can see that California, that the West, because California was really big, this is kind of answering the statistical question, but not answering the logarithmic question. But you can see that there's a lot of variability in the Rockies, in the Northwest, and that makes sense, and in the West. You can see that the upper Midwest, the Northeast, even the Ohio Valley, does not have a lot of acres burned across those states in that region. I'm going to go to a set of things to think about. Can you see the set of things to think about?
It's changing much quicker these last couple of slides.
Oh, good. So where is Delaware? So Delaware and the original data had 0 acres burned. Where is Delaware? How does that fit into the plot? Because 10 to no power makes 0, right? So that's a little problem. And that's something to remember, because Delaware, the person with Delaware must have had trouble trying to figure out where to go. If a state had only 50 acres burned, where would it go in the number line? So pick one of these questions and think about what the answer might look like. So pick one of those questions. Think about what the answer might look like. And then I'm going to go and we'll think about some of those answers. So where would 50 acres go? So you have to stop and think about, what does 10 to the 0.5 look like? So 50 acres is going to be somewhere between 10 to the 1.5 and 10 to the 2.5. It turns out when you do this with students and have them talk in groups and figure out where they would put these numbers, after you have this conversation, some of the kids go back up and move their sticky notes because they have not really internalized what that scale shift has actually done. So they're very used to everything coming in halves. So they think that halfway between 10 to the first and 10 to the second, so 10 to the 1.5 should be the same thing as halfway between the two numbers. And that's not quite how that works out because you've rescaled it. So these are really good thinking questions to get your kids involved. And one of the questions is, what would happen if I used natural logs, if I used log to the base 10, which I did, and if I used base 2, if I scaled it to the base 2. I noticed that the distributions are all exactly the same. So that's a really, I mean, the shape of the distribution is exactly the same. The numbers that you've transformed them to are not. Now, I want to point something out about this, that if you saw the earlier presentation on nuts and bolts, Stephanie talked about thinking about functions and transformations is a really big part of the CED for precalculus. And thinking about the function as a process is a really important idea. And that idea is here in the notion that I'm mapping all of my original acres burned onto these new numbers. So I have mapped or transformed my numbers so that now I can actually have a manageable scale. So stepping back off of this, so our agenda today is to think about an introduction to logarithms, look at an overview, discuss the role and properties of logarithms, explore dice and exponential functions, and investigate regression. So the CED for precalc has both skills and content. And the skills are about multiple representations, procedural and notational fluency, and communication. And those are really important pieces. And having students be able to work through a problem using those three big skills are important. The CED content that we're talking about right here is in Unit 2. There are some new ideas that show up in the CED, and some of these show up overall, and some of them show up specifically in Unit 2. The idea of validating a model, associating rules and transformations, limit notation, the semi-log plot that we were just kind of talking about, and some new vocabulary shows up. So we have in this little exercise that we just went through, we looked at logarithmic functions, we looked at data modeling, and we kind of got to semi-log plots. The next part that we're going to look at is checking about the validity of a model, looking at some exponentials, and thinking about what makes things linear. So before I turn this over to Steve, I just want to give you a couple hints on logarithms. First, why logarithms? So historically, those of you that have been around for a long time know that once upon a time, we used to teach students how to use logarithms to calculate because it was easier to do adding and subtracting than it was to do multiplication or division. So we rewrote numbers so that we could calculate using logarithms all adding. We just saw an example of rescaling the data to cope with very large or very small extremes. Logarithms can straighten data. And there's a very real good reason, which really is more apparent when you study why it's important, what is this idea of an inverse of an exponential function. And the examples down there from the CED, the course and exam description, construct new functions using transformations is an important thing to do. So we're going to look at answers like how can we adjust, or we did look at something about how we can adjust the scale. So here's just a really simple example of the number of ancestors by generation. And you can see that that's clearly an exponential model. If you take the log of the number of ancestors, you will see that it's totally straight. So this is one of the really big powers of what logarithms are good for, is for straightening, is particularly exponential data, but it straightens other kind of data as well. The log properties are important. This is one of my favorite questions. And I just want to show you, because this is a part of the skills, what happens. I could ask you to put this in the chat, but I don't want to spend a lot of time on this. One of the things that's important is this multiple representations as one of the skills in the CED. And if you graph both of the function and the function with the domain doubled, and then if you use your trace, you can do this either on an Nspire or on an 84, you will notice that the difference in the y values is always 1. So the answer to the question is that y increases by 1. But the real thing to think about is, why is that true? So you want kids to think about, okay, logarithms, why is that true? Well, logarithms come from exponents, and exponents have certain behaviors. And if you back it up into the rules, you can see why that's true. Logarithms also relate to this exponential inverse. And so playing with the questions like this and graphing them is another way to help kids develop this sense of what logarithms are and how they're related. I want to point just 2 examples, and then I'm turning it over to Steve. The 2 examples are Gapminder. If you've never seen that, it's a really great site for lots of data, lots of interesting things, and a lot of it is data over time. And one of the things that's really cool is they deliberately allow you to look at their data in a linear scale or a logarithmic scale. And here's the example of income and life expectancy. And you can choose which one you want to choose to look at. And that's the true for all of their data sets. And I think that's a really interesting thing, because what it means is there's a real need in the world that to pay attention to A, the power of logarithms, and B, how to rescale things and why it's important. Here's one last example. This is another logarithmic scale. It was in the media, and it talks about the number of infected people by each sick person. So that's the transmission rate for a disease. And the vertical axis, which is scaled in a logarithmic scale, is the fatality rate. And just take a minute, and what do you notice and what do you wonder about this logarithmic picture? What do you see? What's interesting there? Anybody notice anything? So one of the things that we have to be really sure that kids can do is that they can actually read the graphs. So it looks to me like measles, which is way over here. Measles has a high transmission rate, but it has a fairly low fatality rate. Steve says it looks a bit misleading. He notices, Tucker notices that he doesn't understand it. So this is, if you get the measles is really a contagious disease. So if you get it, you give it away to lots of other people. So it has a really high transmission rate. It affects a lot of people, but people don't die from it. That's what this is actually telling you. However, if you get the bird flu, you don't infect very many people. You have a low infection rate, but a high fatality rate, which means that if you get the disease, you're pretty much apt to die. This would not be possible to really scale on just a normal scale. Have to be put together because it had those extremes in it. It had to be rescaled using logarithms. Hopefully that helps you understand it a little bit. All right, I'm going to turn this over to Steve. He's going to tell me when to change the slides, and go for it, Steve.
Thanks, Gail. This is cool. I loved all the fire data. And that last graph, I'm kind of thinking about that last graph. That was very cool. So I do want to share some resources, like where can I go to find some exponential things or just some pre-calc things that I could use either on my Nspire or my 84. And one of the things I will highlight is this problem of exponential dice. And so, for example, I roll 10 dice, and I'm going to remove all the dice that show a 1. And I'm going to repeat this until all the dice have been removed. So let's enter a number in the chat, but don't press enter right away. Let everyone kind of maybe put an answer in. But how many rolls do you think this will take until all the dice have been removed? Type a number in there for the number of rolls you think it'll take to remove all the dice this way, but don't press enter, but that's okay if you did press enter. Okay, now press enter, go. Yeah, so this is a nice little problem, and it does exist on both for the Nspire already and for the 84. Gail, do you want to go to the next slide? I don't know what we've done, but the slides seem to change pretty quickly. So again, you will get this slide deck, and you'll also get the Nspire file that I will share here in a little bit. But on this is Math Inspired, and what I have done is I've tried to create a different version of this activity exponential dice, which is on their page. But there's also other pre-calculus things that you could use on the left-hand side. It's maybe hard to see, but when you get there, that's where you can search for content area. But this is all of the exponential and logarithmic function types of things. And this exponential dice file actually had a little bit of TI Basic running in the background. And so I decided, this is the computer science teacher and me, I decided to turn this into a Python activity, and we'll share that here in a second. So Gail, would you go to the next slide for me, please? And on this next slide, when it shows up, there you go. This is the activity that exists on the activities page for the 84. And if you're like me, you probably did this at some time in an Algebra 1 class with your students. We did not use coins. We used M&Ms, and we shook a whole bunch of M&Ms, and we removed all the ones that had M's showing up on them. So this is that kind of activity, which also has a little bit of code running in the background. But that is the coin toss for the 84. But also on this page on the left-hand side, there are many other pre-calculus resources that you could draw from and use if you're an 84 user. Gail, do you want to go to the next slide again, please? And so back on the exponential dice. So there were a bunch of numbers. It seemed like the smallest number put in there was 6. that might be from a statistics teacher. And it looks like the largest one scrolling through that was about 25. And so Gail, if you want to stop sharing, and I'm going to start sharing my TI video. I wonder if I share if it'll just kick you off. So so we're going to find out, and hopefully, like, since I can't see the chat now, and but that's okay. Hopefully you guys can see my screen, and I am sure Gail or Donald will jump in if they can't see my screen. So again, I'm an Nspire user, love the Nspire. I think it is like the perfect handheld created for, certainly for, I think for AP Stats, AP Calc, and now AP Precalculus. Great handheld, but the 84 is good too. So you've got 84s around, and those what you use, you can't go wrong with those either. I just prefer the Nspire. So we can actually simulate this kind of slowly by using the sequence command. So what I'm going to do is I'm on a calculator page on an Nspire, and the sequence command is going to create a random integer from 1 to 6, and A is my index, so it's kind of like keeping track of how many times I do it, and I'm going to do it as A goes from 1 to 10. So what I'm actually going to do is create a list of 10 random integers. So when I press enter, there are no ones to remove on this page. So I'll press enter again, and now there are 3 ones, which means I'm going to go up and grab that, and I'm going to change the 10 to a 7 because I'm only going to roll the 7 dice that I have kept. And let's see what comes up here. Ooh, so I'm going to go up and grab it again. So there are 2 ones. And if you are like me, you are probably thinking, oh my gosh, that's 7 minus 2. That's 5. So you're probably thinking there's got to be a quicker way to do that. And if someone would actually ask that in the chat, that would be fantastic. There's got to be a quicker way to do this. And so, yeah, the answer is yes. There is a quicker way to do this. And that is by using I love using a Python program. I love using any program, first off, just because I can do really, really big numbers. But let's go to a Python program and let's see if we can simulate this activity for the 10 dice. And we'll take a look at some of the data that comes with it, and then we'll try some really big numbers, and we'll see what happens with the really big numbers. So I'm going to build my program, which saves it, and I'm going to run the program. And again, you will have this file. It'll probably go out with the rest of the stuff. And so the number of dice that we started with were 10. And the number of sides on each dice is 6. And now this next question, and you got to read carefully, enter the minimum roll value to keep. So if we want to throw out all of the ones, that means the minimum roll value to keep would be 2 and above. So I'll put in 2 for there. And then 2 things are going to spit out. The 2 things are a list that goes from 0 through 9. And the question I noticed popped up in the chat is, can you do this on the Nspire or on the 84? And on that coin activity, I believe there is a program running in the background that could possibly be modified to do this. I just take a little bit of expertise. So the number of dice started at 10, and then 5, 4, 4, 3, 2, 1. And we could do this again. So enter number of dice, 10. And again, the kids are, I think, the kids are usually amazed. They expect it's going to be the same, exactly the same data. And when it's not the same data, it kind of freaks them out, which freaks me out. So there are 11 rolls this time. It took 11 rolls to get down to no dice that are left over. And so now the rate goes from 0 to 10, 0 to 10. But what I like about a simulation using Python to do this is we can do some like really big numbers without really slowing things down. So we did it by hand. That could take forever. If you did M&Ms in your class or actually rolled the dice, that could take a long time. But I mean, you should do that to start with, but then try to jump into something to generate big numbers. So I don't know. I don't know what's going to happen if I put 10,000 in. I'm really kind of afraid. but we're going to find it and see. And then we could use a 6-sided dice again, but that would be no fun. And I think, and I agree with that. I agree. I think doing one dice at a time would also be good. So let's pick just for kicks, let's pick a 20-sided die. And let's keep any number that is 5 and above. So we are going to kick out the numbers 1, 2, 3, and 4. So we're going to kick out 4 numbers, and we're going to keep 16 numbers. So I will go 5 and above. And this might be another thing you're thinking. I would love, I mean, the tables are cool, not as cool as the spreadsheet that Gail shared earlier, but the tables, the list of numbers are cool, but it would be really cool if we could see a graph of this. So it is possible to take this data that you're getting from an Nspire file or an Nspire program, and we can actually graph this. So this is a data and statistics page. And I will hover over the bottom edge and click on the bottom edge. Now, there's a lot of junk going on here. The 2 things I'm interested in are the 3 things at the top: dice counts, L log, and stage. So stage are like the steps, like the first trial, second trial, third trial. So I'm going to grab stage and place that on the x-axis. And then I'm going to go over to the left-hand side. I'll click over in the margin on the left-hand side. And what I'd like to do is grab the dice counts. Dice counts is where that data was saved. And so there is my data. Now, we could do a regression with this. I kept running into trouble with regression because it just didn't like this, but I don't think we need to do regression. I think we could actually build this model. That is an AP Precalc thing, is building models. Am I right about that? So we could actually build a model and see how well the model fits the data, or how well the data fits the model. And we could try this again. So on the Nspire, again, everything starts on the Nspire with the menu button. So if you go to the menu, and I want to, if I want to plot a function, I want to analyze this function. So I'm going to click on 4.
Steve,
Yes.
someone asked how you got the points from the data to show to start with.
So there is a command in the Python that I can send the data from my Python program into the Nspire list. So that is it's in the Python programming, and would love to talk about that more, but that would be like its own hour session. So, but shoot me an email. I'm sure the email will be shared, and then just I can talk you through that. It'd be easy to do. Great question. Oh man, love those questions. So number 4, now I could do regression. That would be the easy way out. I'm just going to do plot function. It's going to work the same way. So I'm going to press 4 again. And so it's waiting for me. Now, if I recall correctly, the dots are the number of dice that are left. And I believe we started with 10,000 dice. And every time we rolled, we removed 1, 2, 3, or 4. So we kept 5 and above. So that means we kept 16 out of the 20 dice. So we should be keeping 16 20ths at each stage. So that is 16 over 20. And we'll raise that to the x power. And so that is the model. I don't know. Kind of matches somewhere, but it looks like it's a little like underestimated. Like my model is not perfect here. Maybe my model is wrong. Maybe I counted incorrectly. But let's look at this. And if I go back to menu and I go back to analyze, since I have a function there and I've graphed it, I could actually show the residuals. And so that's, I know, and residuals is how is the model a decent model? So I'll go to my residual plot. And it certainly looks like early on, there's not a very good fit. But I think as we get further and further out, it seems the data fits a little bit better there. But that doesn't look like a very good fit at all. That's a bummer. But so this is again, one way I can approach this. I love using the Nspire and I love using the Python to make this work. Again, I would love to answer more questions about Python, but that's like its own webinar in and of itself. If you would like to know how I can get that data from Python into Nspire, just shoot me an email. I'll drop my email in the chat a little bit later on. But that is good. So because I want to get to Gail's next activity. So I think, Gail, I will turn this back over to you. And again, if you have any questions, reach out to me via email or find me on Twitter or social media, and I can certainly help you guys out.
Okay. Thanks, Steve. That was pretty cool. All right, so I'm going to share again, and we don't have a whole lot of time here, but we do. We have got plenty of time, I think. All right, so let me figure out how to do this sharing again. All right, come on, share. Slowly but surely, here it comes. All right, so that's where we were with Steve, and I looked through all of these things. Oops, and I am back to get backwards. All right, to my crocodiles. All right, so here's the crocodiles. And here's crocodiles' data on biting. And these researchers from Florida State were interested in looking to see if there was a relationship between bite force and body mass. So the bigger crocs have a stronger bite force. And that picture that you saw was how they managed to measure the bite force, and to me, it looked kind of challenging, but they figured out how to do that. So here is the data, and you can see, it's like, all right, we got all this stuff. And so, and here's actually came from the article that I found this in. And so it talks about the different kinds of alligators and crocodiles, which kids actually get really interested in. And so why did they care? This was actually a real problem that they cared about. So they're trying to figure out how the feeding, how these animals moved, and how they're in search of food, and how the jaw force, the bite force, actually had something to do with the kind of food that they were in. And so they cared. So basically, you could do this on the 84, or you could do it on the Nspire, and just graph the weight or the bite pounds, so the bite force pounds. And you can just do a regression, although you notice one guy is like way up there. So if you just graph and do a linear regression, just punching the button that Steve was talking about, you get this picture. And Steve talked about residuals, and they're a big deal in the course and exam description book for pre-calc. The residuals are the difference between the actual predicted value, in this case, it would be the bite force, and the predicted value and the actual value. Now my thing is, okay, and the actual value. So those little vertical segments are all my residuals. And the idea is to minimize these residuals by your regression line. So you're trying to find a regression line that will minimize those residuals. As a matter of fact, the regression is really about minimizing the sum of the squared residuals, because you have to account for over and under. So you want to minimize the sum of squared residuals, and the squaring gets rid of the positive and the negative. And so we have this this residual plot. We've got this idea here. And basically what I've just done here is transformed by taking the log. Remember, one of the things we like about logs is that it straightens data. So in this picture right here, this is the original data and the residual plot. In this picture, this is the, I took the log, natural logarithm of the bite force. So I left weight alone, took the natural log of the bite force. This picture, I took the log of the bite force and the log of the weight. So I took log of both of them. And in this picture, I just took the log of the weight and not of the bite force. And so the question that we have to consider is which of these models is going to be the best model for the bite force and the weight of these crocodiles and alligators. So when you look at this, what are you guys thinking? See anything? What are you thinking? Yeah. So the idea here is that you have a good model if there's no pattern in the residuals. So if there's a pattern in the residuals, then your model really is not good. And then that graph that Steve had before, there was clearly a little pattern in the residuals. The graph that Steve had about how many in the exponential model that he used to fit that. There was a pattern in the residuals. And so one of the things we could maybe try to do is figure out for that problem, all right, maybe I just need to tweak that model a little bit. How can I tweak that model to see if I can get a better one that'll eliminate that pattern? Because the pattern was, for the beginning numbers, it was really not very good. And then as the fit got better as the number of trials went on. So we want to try to figure out which one of these might be good. I see somebody said LN bite. So that would be this one. Looks fairly good. So see this one, like it seems, except for that one guy, there's a pattern there that after you get past here, in terms of weight, everything is below except that one person. So that's not a very good model. This one over here is not a very good model because on this side, everything is above, and on this side, everything is above, and in between, everything is below. So your prediction, if there is a way to make a prediction about a residual, about will what you're looking at be over or under for your prediction, because you're looking at what's going on in this plot, then that's not a good model. So you're trying to figure out a model that won't let you make a prediction about being over or under. So I'm thinking here that this something to do with LN bite is going to be the better model. Either this one be taking the logarithm of both of them, or this one taking the logarithm of just the bite and leaving the weight alone. I think you could probably have a good discussion about that. I'm actually tending towards this one as having a little less pattern in the residuals, but you could probably make a case for either one. So notice one thing that I haven't talked about. Oh, can I please specify which graph? Okay, so this graph right here, the second one on the picture on the left, where you have the LN bite as the label, is not too bad. I would opt for one that had both of the LN of the bite and of the weight, and that would be this one, which is the third graph in from the left. And to me, that pattern, there doesn't seem to be very much of a pattern in those residuals. It looks much more scattered. Here, it doesn't, it looks more like there's a slight pattern in here. But that's what happens when you're modeling, is you have, one of the things that would be important to do is to go backwards. One of the things that would be important to do is to go collect some more alligator data and see if, and this is what they're actually doing now when they do what they call predictive modeling in data science. They would collect some more alligator data and then decide which one of these two models might be the better model to use in general once you had more data. And notice I'm using LNs. We looked before at the pictures and we wouldn't really care if we used the natural log, if we used base 2, if we used base 10. The end result would give you the same picture. The numbers would be slightly different because obviously we're using different bases for our logarithms, but so we really wouldn't care. Mark has a really good question. Shouldn't the relative magnitude of the residual be considered? And Steve answered a fanned residual plot. And yes, if you have a fanned residual plot, that's a pattern, and you can see that a fan would go like this or like that, and you could see that as the domain elements grew, either the range elements continued to get farther and farther apart, or the other way, the domain elements got closer and closer and closer together. And actually, if you were to graph these in the reverse order, so if you were to put byte on the horizontal axis and pounds on the vertical axis, you can actually see really clearly a fanned model that would not be a good model. So you can actually see the fanning, and you can say why that wouldn't be a good model to have. So we could use any one of our bases that we want to. Those of you in pre-calc, students might wonder why you use natural log. And the reason you use natural log is basically, I think, a calculus reason. And that is because the natural log is the only one whose derivative and integral are the same thing. So that's a very big deal in calculus and a very important relationship. And the idea that this is the only function that has that property makes it a really important property in calculus. So we also use it in lots of other situations just because of that property. But it shows up in a lot of the work that we do in pre-calculus as well. So basically, one other thing that I haven't even raised and is not a part of the CED, but people tend to think it is the idea of correlation. So correlation is a numerical value that measures the strength and direction of a linear relationship. Correlation does not tell you whether or not a model is a good fit or not. Correlation tells you how the data, the overall picture of the data are arranged. One of the best things that if you are struggling with the role of correlation is to think about, there's a set of data called the Anscombe data, ANSCOMB, Anscombe data, and it gives you 4 distinct data sets such that the correlation is the same, the linear regression is the same, and the graphs are totally different. One is a straight line, one is a parabola, one is a scatter plot, and one is a straight line with one outlier. And so correlation is a measure only of the kind of strength of a relationship and the direction. R squared, on the other hand, tells you something else, but R squared is not part of the CED for precalculus. So it's not something that you need to bring up when you're working with your precalculus students. So any questions or comments? And then we're turning this back over to Donald so that he can wrap up the session. So if you have any questions, put them in the comments and I'll stop sharing and turn it over to Donald.
Thank you, Gail. I just wanted to remind everyone that the presentations will be available next week and they'll be sent to you. And I wanted to announce the door prize winner, and that would be Larry Hightower. So someone will be reaching out to you, Larry, to send you the technology of your choice. And we would like to thank you all for attending and hope you have a good rest of your day. Thanks, Gail. Thanks. Appreciate you guys. Have a good day.
Thank you, guys. Thanks for being here. And again, you can reach out to either Steve or I, and we will be glad to answer your questions. And we'll make sure that we get everything that was shared on this session, including the data sets and Steve's programs, to the TI folks so that they can be posted.
Yeah, they'll post them on the website and make sure they're available for everyone. So thank you guys for attending.
Thanks,
Steve,
everyone.
thanks, Gail. Very good.
Oh, wait, I have a question. I have something to answer. Elena said, do I have a website where you have activities like these? There are two websites. One of them, actually, I was going to say this before. One of them is like building concepts for middle grades mathematics. In statistics and probability, there is a linear relationships activity that shares these activities in there for the Nspire. Then there is on both for the 84 and for the Nspire, there is a modeling set of activities that are available on the same place that where Steve was pointing out some of the other activities. And they're called mathematical modeling. There's one similar to the one that Steve did with the dice called Hog, the game of Hog. And then there are a whole bunch of other activities involving different kinds of data sets that you can use for mathematical modeling. Many of them have been worked out as activities. Some of them are just big data sets that people could explore. So they're available on the TI website for your use.
Yeah, for Math Inspired is mathinspired.com, and 84 Central is the 84 activities. So you should see those by clicking on the subject.
Thanks, Don.
Thank you,
And
guys.
thanks for that question. That was a great question.
Thank you.